presentation. So welcome again, Josh Dimasaka, and I hand over the word to you. Thank you. You can share the screen and then start with the presentation, and we will continue then with questions and answers later on.
Right. Thank you, Manfred, and thank you, Landwehr, and for our listeners today, spending the time with us to hear what we do at Cambridge. Just to give more context on the slide 6, it says assessing the temporal exposure and physical vulnerability dynamics. So that is the topic of my PhD. It's quite slightly different from what I did at the AGU in December. It was my Master of Research project, and so, but they are somehow related to each other. But I'm doing for my PhD the phrase that you have on the Google slide, the temporal exposure. It's a different topic that I'm doing right now. But yeah, really excited to share with you my AGU presentation on the application of AI to early warning system, mass movements, and landslides. All right. I'm gonna share my screen there. Share screen. PowerPoint. If you, no, that's not it. If you haven't watched my, I also uploaded a YouTube recording version of my AGU 2023 presentation. It's going to be the same, but I'll add more information to it. All right. So to begin, I guess it's best to start the presentation with what was it like during the conceptualization of this problem. Supposedly, it was just a master research project to be done in 3 months, but when we were thinking of a good problem, I think the best picture to illustrate our motivation is this picture. And as you can see here, we got a mass movement. And what's more interesting to see here is that the mass movement disrupt those roads connecting the settlements. And so currently, what we have, or how we do it in the disaster risk community, is that we assess the exposure of these houses to natural hazards like landslides, to mass movements. And so we thought of maybe what if we advance the exposure assessment in a way that we consider the underlying connectedness of these houses, of this settlement groups. So imagine like a social media, like you have the social network connecting them all together. So you have this imaginary graph network. Sorry. Okay. Well, is there like a quick question? All right. But yeah, as I was saying, we tried to conceptualize or imagine what if we consider the underlying connectedness of these settlement patterns connected by roads. Oh, so this picture is the 2020 Gjerdrum incident in Norway. So I took this picture, one of the drone image of the devastation aftermath. And so we all know that one of the triggering mechanisms of mass movements, such as avalanche, landslide, is rainfall. And so it's not new to us that the rainfall is increasing through the years, and we have a very saddening future in the next decades. So it's really important for us to think about how we assess exposure and to give more information about risk information, as the Norwegian authorities also stress out in their calls after the incident. And so the method that we try to develop here can be applied to other areas, but we take Norway as one of an interesting story because one, it has all the data set, and also to illustrate a case study on the use of this method that we're trying to develop. So what's actually really on the ground in Norway? So currently what they have been using is this warning reports, very low, low, high, and very high. This is good because it has undergone thorough work on 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 sorry on early warning system. It's easy to communicate to the public given those colors, green, yellow, orange, and red. And so, but when we look at the technical reports and how they did it and how they derive this warning system, one of the admissions that they have is that one, it is highly conservative. So how they do it is that they have a table, a matrix where you have this daily rainfall, and then you have this static susceptibility map, and then you come up with a warning just by having, like, imagine a lookup table or like a matrix of mapping what is the most visible warning for that day and for that time and for that location. Another admission of the limitation of that warning system currently is that limited refined information. And I guess this is also the case for other countries because one, the challenge of data and how we compute this. And so currently what we have is the warning is currently expressed at the level of city or county. And so if I'm a commuter, I want to know how to re-strategize my commute to go to the city, to the workplace. So it's really important to know how this warning is aggregated at the level in a more refined way, maybe along the roads or maybe along the streets. And another problem is the complex region-specific characteristics where there are areas, maybe the northern part and the southern part of Norway, that have intrinsic differences. And so that kind of maybe correlation or separate treatment should be taken into account when we analyze these kinds of natural hazards. And so the thought process now becomes, so if this is the challenges that we face, so this is the things that we would like to come up with. So instead of four warning signals, what if we try to use a regression to estimate that warning level from 0 to 100%? And I guess this is the most exciting part of the presentation is the use of the big data sets of roads and the settlement patterns. So you are probably aware of some efforts that were done by OpenStreetMap, by Microsoft or Virtual Maps Foundation. They have been building data sets, gigabytes of roads and settlements available to everybody. And it's really nice to incorporate that information to our disaster risk analysis. And the last one is try to model that spatial correlation. I'll talk more about this as we move forward. And there comes the intergraph representation learning. Just an overview of this technique. So there are only two parts to this. One is that we use the supervised ensemble graph neural network to come up with a daily warning or susceptibility map of Norway. And then the other one, I'll talk about the details later because we'll go back to that. We will revisit that. And the second part is using that information, integrate that with the settlement patterns in the roads to understand exposure. And we call the unsupervised spectral graph clustering. The purpose of doing that is to know which of the settlement is most at risk of being cut off from the network. And so just to highlight those 3 points that I just mentioned, the challenges and the solutions. So this particular point or part of the first part, the use of the attribute aware graph and neighborhood aware graph or graph approach in general, this is how we incorporate similarities and maybe some correlation between or among points on the map. I'll talk more about that, but that's how we address the third question, the third challenge. For the first challenge is the use of ensemble in the neural network. It enables us to come up with a regression values, a prediction from 0 to 1. And the last one is the use of the big data sets, 4,800 settlements for the entire Norway, settlement groups, and this road data set for the entire Norway to aggregate the information further. All right. So to give you the intuition, because Manfred also debriefed me about some of us are not familiar with the machine learning. Me, myself, I am new to machine learning. My background is in civil engineering, public policy. So we will do an exercise on intuition to how we use the machine learning here. So this is the map of Norway. And for us to better visualize that, this is the city of Tromsø. Yeah. And then as a GIS person, it's important for us to have a consistent representation of all the variables on the map. And so we use the 1 kilometer resolution. And this is the most feasible using the computer that we have at that moment. 1 kilometer resolution. And for every 1 kilometer resolution, we have temperature data. It's daily recorded or daily estimated rainfall, snow water equivalent, snow amount, snow depth, steepness or slope, lithology, land cover. All of the data sets are open access, and we got this from the Met Norway data online database. And so for us to guide the machine learning model or the model, the statistical model we want to do, we also use an inventory of reported mass movement since 1957, over 69,000 or more or less 69,000. And we use a simple approach where we just basically rasterize those point data into 1 kilometer box, a binary map. If there's an incident, then there should be a 1 signal. And if there's no event or there's no incident, then it's 0 or it's nothing, an empty set. And to fill all the points on the map of Norway, we would be needing 508,000 points or grid box of 1 kilometer by 1 kilometer to cover that. And so that is quite challenging to us. And so this is an interesting point to talk about the data set, because that's going to be a very big data set, given that we have 508,000 rows or points to be supplied or to be used. So as I also said before, we have this information from the flash. We have the temperature, rainfall, blah, 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 up to land cover, all those 8 variables. And the last one is the label that it actually occurred, the mass movement. And so the way machine learning people did this is that they arrange it in a vector format, or in this way, where the first 8, the covariates, the indicators, are called the feature vectors, and the last one is the label vector that will guide our machine learning model. And so because we have 500,000 or more than 500,000 points, and we will have this very tall feature and label vector, very tall and feature label vector. And so during that moment, when we were trying to do the experiment, we didn't have the perfect computer to process all those 500,000 data rows. And so we subdivided into 32 smaller data sets so that we can have a more manageable batch of data or smaller data sets to process. And so for every 32 that's randomly subdivided, every smaller data set, we further split that into training, validation, and testing. And the purpose of this, for training is used for is used for the learning of the machine learning model, or for the training of the machine learning model. This is how we derive the coefficient values and the parameters. Imagine like a linear regression. The validation is the set where we check whether a result is overfitting or not, or if that machine learning model is just memorizing the training data set. And so the validation set's role is to check whether it's overfitting or not. And the testing is another expression of the performance of our machine learning model for samples that are not, or that have not been seen by the machine learning model. And because we have this 32 smaller data sets, so we will come up with, each of them will have their own machine learning model that comprises the entire ensemble of that prediction system. So this is I'm sure you have seen this icon of a neural network where every point goes through different layers and come up with a single value. And the machine learning model that we are using here is a graph neural network. Neural network is what you see on the screen right now, but the graph here, we will define it now. So the graph here is, if you could remember, every point on the map has information about latitude and the longitude, locations, the sense of the neighborhood, and also information about the feature vectors, the temperature, the snowfall, the rainfall, and other features that we just mentioned. So imagine 10 samples of that 1 kilometer and 1 kilometer grid. And so if we measure, if we estimate or calculate the Euclidean distance or the distance between them and set a threshold, and if they fall below that threshold, we build a connection. And so we call this the neighborhood aware graph because they're close to each other. And they're close to each other. And it's an expression of, if they're close to each other, like a spatial correlation, they should have similar information to be propagated or to be updated or to be learned during the process. And imagine the same 10 samples of that. In the feature vector, there's this parameter called cosine similarity. Cosine similarity is a metric where its purpose is to measure the similarity of various features like snowfall, rainfall, temperature, and it gives 0 to 1, 1 being a highest, like most similar between each other. And so if they are very similar to each other, and if it's set a threshold, then we build the same graph where we connect them together. So the neighborhood aware graph and the attribute aware graph can be different, but it's an expression of how similar or how like the proximity to each other is. And so as we train the neural network, every time we train this on the right side, like for every step of the way, it propagates the update to every neighbor or to every link or to every node that it has around it. Like for example, this one. So whenever there is an update to the neural network as it trains, so the associated change to that neural network is propagated around it. And so that's the intuition about graph neural network, where we encode some proximity information or maybe similarity information, and then use the power of neural network in estimating that fitting. I can talk more about graph machine learning later if that's confusing. And so in the end, so imagine we have 32 graph machine learning models. We will have 32 predictions of probability of mass movement given that. And so if we try to plot that histogram of the 32 predictions, we can have a sense of like a distribution of what's the most likely value for that point or for that location, for that prediction. And so there's an example of a daily mass movement susceptibility or a warning map, where I think this is the average, like the average value from that histogram. And so revisiting this mass movement incident that I just shown to you in the beginning. So another one problem that we had during that time is that the current warning system, they gave no danger and low warning for the region where there was actually an accident. And so we tried to estimate using our model, and it shows some value to it that could be somehow informative to the people, to the residents. But I know there should be more work on this before we realize the use of AI or machine learning into practice. To give you a sense of how accurate this model is, so there's this curve that we call ROC curve, or the receiver operating characteristic curve, where it's a graph or it's a plot between true positive rate and the false positive rate. And the prediction models was able to achieve 86.25% area under the curve, which means it's able to distinguish a mass movement compared to a simple line, diagonal line, which is the simple diagonal line is a random guessing capability of any machine learning or any model. And so having been able to get 86.25% is just shows that we were able to distinguish a mass movement or not from that. Okay, my internet connection is unstable. Let me know if I'm lagging. All right. So to the second part of the word. So now that we have the susceptibility map or the warning map of the entire Norway, the second part is the integration of the information of the exposure, the road network. So again, this is the city of Tromsø. And what's overlaid is the susceptibility map that we just estimated, 1 kilometer by 1 kilometer. We have the formal settlements data and the population data associated with it. And one of the problems that we face here is that in order for us to realistically model the road networks, we have to reduce the resolution from 1 kilometer to 50 meters. Because if it's 1 kilometer, then it will just give you lots of coarse 1 kilometer box, which is not really informative. And so there comes another challenge of computational complexity because we have to use more refined resolution, which is this one. And there's this graph representation approach called simplicial networks, where you create a connection between 2 points or between these 2 circles if they are adjacent to each other in all directions. So for this case, we try to model the road network as simplicial network, where from this representation, we were able to the shortest path possible between any 2 settlement groups. And with that information, we were able to simplify the representation of the settlement groups like this. Like if you have settlement A, B, C, D, and F, and they're just linked by a single shortest possible path. And because we know the profile of that shortest possible path, we can also know what's the highest susceptibility value along that path. And so these are the illustrative values that we have. So as you can see, we have a very high susceptibility value between settlement C and settlement F, which is 0.44. And then given that situation, we wanna analyze the profile of every exposure. And so we thought of maybe we can do some kind of clustering approach. And so what we did is we introduced a susceptibility threshold from 0 to 1. And as we increase that from 0, then 0.1, 0.2, up to 1, we try to observe the behavior of the settlement networks. So, and see which one is cut off from the social network or from the settlement network. And the lowest cutoff value that was able to cut that link separating one settlement from the rest, that results in the isolation of the settlement from the graph is what we called, or what we minimum probability to trigger that inter-settlement isolation, given the roads being susceptible to the mass movements. And equally important to this, it's a very simple approach to analyze. There's a lot of ways to do the clustering and lots of possibilities. I'm happy to answer that, and we could discuss that later. But that is an initial work that we did. But equally important to that aspect where we analyze the inter-settlement isolation is the intra-settlement exposure probability. So we can have 2 separate values of exposure probability to the mass movement. And to illustrate that, so there are 2 stories here. One is the village of Lynage and the village of Bradbag. So here, we have a low inter for the village of Bradbag, which is 35%, compared to its intra, which is 53%, because as you can see on the map, it's very well connected to the network of settlement around it. So the way we think about this, it's like, it's an expression of how connected the settlement is with respect to its surroundings. Compared to the Lynage, which is this one, it has high interprobability because it's very remote to to the group of the settlement networks. And all in all, we have this daily warning map. We have this assessment of all settlement groups in near real time, because it doesn't take much time to do this, as long as we already have a trained machine learning model and just doing the downstream processes. And that's all we have. And if you are interested in the code and the data, you can save this. I'll provide this information, but you can save this DOI code, and happy to answer any of your question. I hope I'm under 20 minutes, but happy to take answers. I love driving the conversation.
Yeah, great.
with
Thank you
more
very
questions.
much, Josh. And I'm turning off now the recording.
Thank you.